Okay, then let's start. 네, 안녕하세요. 성균관대학교 양자정보연구지원센터의 김준기입니다. 지난 이제 한 달 동안 저희 퀀텀 챌린지 이벤트를 이원큐와 같이 하면서 문제들을 공개를 하고 또 이제 좋은 문제들을 잘, 이제 참여를 해주셔서 감사드립니다. 오늘은 이제 그 마지막 시간으로 세 번째 문제의 이제 해답을 공개를 하면서 여러분과 같이 이제 문제 풀이를 하고요. 그리고 문제풀이 마지막에 저희 이제 최종적으로 이벤트의 이제 우승자, 누가 이제 수상을 하시는지에 대한 수상자 명단을 공개하는 시간을 갖도록 하겠습니다. 우선 첫 번째로 세 번째 문제를 데니 다을 박사님께서 내주셨는데요. 이 문제에 대해서 문제 내용과 이제 문제 해답을 같이 들어보는 시간을 갖도록 하겠습니다. So Danny, mic is yours. You can start solution.
Great. Thank you very much. It's good to meet everybody virtually. I'm going to start screen sharing here in just a second. Um, is this good? Can people see my slides?
Looks good, Danny.
Great, thanks. So the problem that I put together here is what's called a Heisenberg spin glass. And the idea is to define a model, a quantum physics model that would really be of interest to a condensed matter theorist, and then to use some techniques from quantum computing to analyze the model. And so I'll start off just defining what I mean by the Heisenberg spin glass. This is what you see in this callout box here on the right side of the slide. I'm first defining an interaction term that I call Hij, and this is an interaction between two spins, spin I and spin J. And you can see that it has the product of sigma x operators, sigma y operators, and sigma z operators. So it's a symmetric interaction between spins I and J. And then the Heisenberg model combines these kinds of Hamiltonian terms with a weighting factor, Jij, for pairs of spins. So this is what I mean when I say the Heisenberg spin glass. And so what we're going to do is take this model and analyze it in a few different ways. The first thing I'd like you to do in part one is just classify the possible models that you could have if we just have four spins. I'm choosing a four-spin model just to make our analysis a little bit easier. And then in part two, I'd like to apply adiabatic evolution. I'll say a little bit more about what that is. Adiabatic evolution to find the ground state of this Hamiltonian. And then the idea is to try to turn that adiabatic evolution into a quantum circuit, and then approximate the depth of the quantum circuit, and then decide whether that approach would be a realistic way of building the ground state for the Heisenberg model. And then in part three, we're going to take a different approach, what I'll call a direct approach, and we'll just try to build the ground state directly for the Heisenberg Hamiltonian using what I call XY mixer operators. These mixer operators have a very interesting property. They kind of effectively move spin probability amplitude between two spins, but they do it in a way that conserves the total spin of the system. And so it turns out that because the ground state of this model lies in a sector with a fixed total spin, what we can do is first move our wave function into the correct spin sector, and then we can use these XY mixers to kind of effectively shift around in that spin sector until we hit the ground state. So that turns out to be a much more efficient way of getting to the ground state of the Heisenberg Hamiltonian. We'll then compute the ground state energy after we've built the circuit. So this is the set of steps that we're going to follow in the exercise. Let's see. Now, on the slide here, I'm addressing the first part of part 1A, and I'm showing what the symmetry classes of the Heisenberg model are. So these diagrams here, let me explain them. Each one of these diagrams has four spins. They're the four nodes here. And then there are six lines, all possible interactions between the four spins. And I've drawn the interactions as either blue or red. And let's pretend that blue means ferromagnetic and red means anti-ferromagnetic. So that means I'm just flipping the sign of the Jij coefficient from -1 here to +1 over here. So it turns out that you can actually figure out what all the symmetry classes are purely using graph theory. You don't actually have to write down the Hamiltonian and compute its eigenvalues. So that's what I'm doing here in these diagrams. What I'm doing is I'm starting with a model that has purely ferromagnetic couplings. And since there are a total of six couplings in all, I can effectively divide all the models based on how many ferromagnetic couplings I have. So I could have six, or I could have five, or I could have four, three, two, one, zero. And so what I'm doing here in this slide is just drawing the possible ways that I can arrange, one ferromagnetic coupling and five antiferromagnetic couplings, or three ferromagnetic couplings and three antiferromagnetic couplings. And so it turns out that the symmetry classes are actually fairly easy just to construct this way. If all the interactions are ferromagnetic, there's only one way that you can put them together, and that's what this picture represents. If you turn one of the interactions into an antiferromagnet, it doesn't matter which of the six it is. So all six of those possibilities are represented by this one class here. If two of the couplings are antiferromagnetic, then the two couplings could either share a spin, which is what you see here, or the two antiferromagnetic couplings could be between different pairs of spins, like you see here. So I just classified all of these different permutation possibilities. And then the big blue arrows are the so-called sign flip symmetry. That's when I change all the ferromagnetic couplings into antiferromagnetic ones. So if you only count the permutation symmetry, there are a total of 11 symmetry classes. That's two here, two here, two here, two, two, and one. But if you also count the sign flip symmetry, then these two become the same, these two become the same, these two are the same, these two are the same, these two are the same, and this one is actually sign flip invariant, because if I turn these three antiferromagnetic couplings into ferromagnetic couplings, I can then permute the spins, and I can convert that into itself. Oops. So at any rate, whether you said 6 or 11, I really actually gave you full credit for answering this problem here. Now, the next thing I asked you to do is to compute the eigenspectrum of each of these six symmetry classes. And so in this table here, I'm labeling the symmetry classes S1 through S6. Is there a question? Okay, I'm going to keep going. And so for each of the six symmetry classes, I'm listing the Jij coefficients, and then this is the eigenspectrum. And you'll notice that the eigenvalues typically are repeated, and that's very important. So you need to count the repetitions of the eigenvalues. If two of the eigenspectra match, but the number or the degeneracies do not match, then I would not say that they actually match. So one thing that's kind of interesting is the symmetry classes S1 through S5, all of their eigenvalues are integer values. It's only S6 that actually has some non-integer eigenvalues. And S6 is the one that is sign invariant. So if you flip the signs of all the Jij coefficients, that means that you're flipping the signs of all these energy eigenvalues. And you can see that the minus 6.9 turns into this positive 6.9, and so on and so forth. So this is the only class that is actually sign invariant. Okay. Now, these graphs are from part 2A. So what I'm asking you to do in this part is to do a so-called adiabatic evolution. And what that means is that we imagine that we've got a time degree of freedom here. And this is at the beginning of our system, we have a very simple Hamiltonian. And then as time progresses from 0 to 1, we interpolate linearly between a simple beginning Hamiltonian and a more complicated final one. So these 6 graphs correspond to the 6 symmetry classes that I showed you on the last slide. So this is S1, S2, S3, S4, S5, and S6. And S6 is the one that has a sign invariance in it. So if you actually take this plot and you flip it upside down, you invert it around this line here, you'll see that these eigenvalues change places with the ones up here. But in each one of these plots, we're interpolating between a very simple Hamiltonian at the start and this Heisenberg spin model at the end. And the simple Hamiltonian that we're starting off with is the sum over all 4 qubits of the sigma x operator. So that Hamiltonian is actually a sum of independent terms. And that means that really what we're doing is we're diagonalizing 4 independent Hamiltonians. Each one of those Hamiltonians, the sigma x, has a +1 and a -1 eigenvalue. So it's actually very easy to see the spectrum here. The spectrum goes from -4, -2, 0 to 4. And the degeneracies across here are exactly what you see in a row of Pascal's triangle. So the degeneracies would be 1, 4, 6, 4, 1. And it's interesting that the eigenvalues actually interpolate linearly between the starting point and the ending point. And this surprised me when I first saw this, but the reason for this is because this starting point Hamiltonian, the sum of the sigmas, actually commutes with the Heisenberg spin model. And because of that commutation, these eigenvalues actually interpolate linearly as we kind of go from the starting point to the ending point. Now, the reason that I wanted to have you plot these out is because for the adiabatic evolution, we require a couple of things. First of all, this point here is what we call a crossing. And if there's a crossing in the ground state as you go from the beginning to the end, then you typically will lose probability into this excited state here. So if you see a crossing like in this graph or this graph here, or this one down here, then the adiabatic evolution is not going to do a very good job producing the ground state. And the other thing that I wanted also is I wanted a unique ground state at the end. And so the reason I wanted that is because if we do this evolution, I want to be able to make sure that we hit the unique ground state and we don't have to worry about these other degenerate states. So if you look at all if you look at all 6 of these symmetry classes, every one of them either has a crossing like you see here, or the ground state of the Heisenberg spin model is degenerate like you see here. So I did not want to use any of these symmetry classes for the next part of our exercise. Instead, I wanted to perturb our Hamiltonian a little bit so that we remove the avoided crossing. There's a gap here, and so that the final ground state is unique. And so to do that, what I did is I altered the Jij coefficients in the Heisenberg part of the Hamiltonian. Here you can see the altered Jij coefficients. And then I also included linear terms here. That's the HI sigma z's, and here are the HI values. So this is the Hamiltonian that we're going to analyze for the rest of part 2 and part 3, okay? Now, this is when I actually did the adiabatic evolution of that Heisenberg Hamiltonian. And what I'm trying to do is match the exact probabilities in the ground state. So these are the 16 computational basis states, 0 through 15. And you can see that if I actually exactly diagonalize that Hamiltonian, out of these 16 states, only 4 of them actually have any probability in them. State 7, state 11, state 13, and state 14. So what I'm going to do then is do adiabatic evolution, and the adiabatic evolution is governed by the total time and the number of time steps. And then I'm going to compare the probabilities that come out of the adiabatic evolution with the exact probabilities. So when my time is set to 10 here, you see that most of my probability is still in state 15. And I'm really expecting to have state 15 with no probability in it. So this is not enough time. I've got to do my adiabatic evolution more slowly. So let's go from time equals 10 to time equals 100. And now you'll see that the probability in state 15 has dropped to 0.44. So that's good, but it's not good enough. So again, let's increase the time by another factor of 10. So I go from time 100 to time 1000. And at this point, the probability in state 15 has dropped to 0.000318. So that's very close to zero. It looks like it's probably good enough. And if we look at the other states that have significant probability in them, that's state 7, state 11, state 13, and state 14. And those four states match pretty closely the exact probabilities over here. So this is enough time for our adiabatic evolution, and I'm kind of arbitrarily using 10,000 time steps. So then the last part is how many gate elements would it require in a quantum circuit to actually mimic this adiabatic evolution? And so in order to mimic the adiabatic evolution, we have to take our Hamiltonian and exponentiate it. E to the minus I tau h gives us time evolution of the Hamiltonian h. The Hamiltonian consists of x terms, y terms, and z terms, and these turn into rxx gates, ryy gates, and rzz gates. And since there are a total of 6 spin pairs in the Hamiltonian, each one of these gates appears 6 times. And then the Hamiltonian also has 4 linear terms in it, the RZ terms, and there are 4 of them. So in all, each time step of the Hamiltonian will take 3 times 6, that's 18, plus another 4, that's 22 gates for one time step of the Hamiltonian. And then the mixer operator has RXs, and there are 4 of those. So 22 plus another 4 gives 26 gates for each of these trotter steps. And we have a total of 10,000 trotter steps. So 26 times 10,000 is about 266,000 gates, which is way, way, way beyond the capability of any modern NISQ machine. So this is not a good approach for creating the ground state of the Heisenberg spin glass. So now we're going to go on to part 3. In part 3, the main idea is we're going to take advantage of the fact that there are only 4 states that have non-zero probability. And all these 4 states are in this part of the Hamiltonian or the Hilbert space that has Hamming weight 3. In other words, 3 qubits are turned on and 3 qubits are turned off. So if you'll remember on the last slide, I called out the states that appear. There's 7, 11, 13, and 14. So if you write down those 4 numbers in binary, then you'll see that you're going to get digit strings 1110, and the bit ordering here is this is the least significant bit, this is the most significant bit, this is the opposite from Qiskit, but this is 7 in binary, this is 11, and this is 13, and this is 14. So our ground state is going to be some linear combination of these 4 states. So the idea now that we're going to pursue is let's start our system in one of these 4 states. It doesn't really matter which one. We'll pick one. And then when we start the system there, we can use these so-called mixer operators, these MIJs. And what these mixer operators do is shift probability back and forth between a pair of qubits. So in this example, M23 can shift probability between qubit 2 and qubit 3. So if we start with our system completely populated in the 1110 state, we can apply the M23 mixer and move probability from this state into the 1101 state. And so this little diagram here shows us that the 6 mixer operators each move probability back and forth between a pair of states. So the main idea then is we will start by creating a quantum circuit that initializes us to a state like this, and then we'll use some of these mixer operators to spread our probability from here over to here and here and here. And so this little graph here tells you right away that certain sequences of these mixer operators will actually work correctly and other ones won't. So for example, if I used the sequence of mixer operators M23 followed by M02 followed by M23 again, that won't work. And the reason it won't work is because M23 can move probability back and forth between these states. M02 can move it back and forth here, but nothing has allowed us to move probability over to this state here. So whatever pattern of mixer operators we choose, we need to make sure that we can reach all 4 of these states from some initial starting point. And so the sequence of mixer operators that I used when I worked out the problem is I first populated my system into this state here. Then I applied mixer M03 to move probability down here into this state. And then I applied mixer M01 to move probability over here. And then I applied mixer M02 to move probability up here. So my sequence of mixer operators was M03, M01, M02. And then the tricky part here to this exercise is figuring out the angles that you need to apply or supply to each of these mixers so that you move the correct amount of probability into the target state. So here's a little bit of code that I wrote that performs this operation. My main routine here sets up the target probabilities, and these 4 numbers here should look familiar to you. These are the probabilities that showed up back here in this chart right here. So this is what I'm aiming for, and I'm trying to find the right angles in my mixer operators that will take me to these probabilities here. So this is my target. Then I'm going to use the minimize routine from SciPy, and minimize is going to change the angle parameters for my 3 different XY mixers. And if I choose the angle parameters correctly, then the output state should match these probabilities. So when I call the minimize function, I hand it this function f, and this is what it's trying to minimize. And here's my definition of the f function right here. It takes in the angles for the mixer operators, and you can see the ordering of my mixers right here. There's the 03 mixer, followed by the 01 mixer, followed by the 02 mixer, and then the 3 angle parameters supply the angles for these 3 mixer operators. And then you see here a little loop where I go through the 3 different rotations, and I apply the XY mixer, which is actually defined in a separate module called HSG rotate. And then once I build the mixer operator, I apply time evolution through a time, and that time is just exactly the angle corresponding to that mixer operator. So I do this loop 3 times, I get my final state out, and then I compute the norm or the distance between my final state and the target probabilities. And the norm is just computing it takes the difference of the 2 states and then computes the L1 norm, which is the absolute value of the target probabilities minus the probabilities from the final state. So this is the computation that actually finds the angle parameters for me. And then here's the output from running this program. The first few lines of output come directly from the SciPy minimize routine, and then it reports these angle parameters to me right here. And then in green, this is the final probability amplitude, not the probabilities, but the probability amplitude of the final state. And you can see that there is exactly 4 of these states that have non-zero probability in them. And so now if we compare the result of the XY mixer with the target eigenstate, so the difference here is now I'm looking at probability amplitudes, not probabilities. So if you square the numbers that you see here in the target eigenstate, if you square them, you'll end up with the numbers that you see over here. So these are the probabilities, and now over here are the probability amplitudes. And you can see that the probabilities are matching perfectly. The amplitude here is the same. The amplitude in state 11 is the same. The amplitude in state 13 is the same. And in state 14, I've got a number which, when I square it here, this is an imaginary number. When I square this, it will match the square of this number here. So the probabilities are correct now, but I have a phase mismatch. And this phase mismatch comes about because when I apply these XY mixers, it always adds a phase to one of the output states. And it turns out that this phase mismatch can be corrected by applying an RZ operator to qubit 0. Depending upon the sequence of XY mixers that you chose and the ordering in which you apply the XY mixers, you will find typically a different phase mismatch. So you'll have to have a different sequence of RZs to actually correct the phase mismatch. And in fact, at least one of the submissions did not use an RZ to correct the phase mismatch, but it actually used a CZ gate, which was very interesting because there were 2 states that needed to be corrected in that submission. So that was a very interesting alternative. And so here is my final quantum circuit that produces the correct ground state. This is the 3 X operators that take my initial quantum state and move it into the Hamming weight 3 sector by turning on qubit 0, 1, and 2. Then the first XY mixer that I'm applying is between qubit 0 and 3. The second XY mixer is between qubit 0 and 1. And then my third XY mixer is between qubit 0 and 2. And if you're paying very close attention, you'll notice that these angle parameters here are actually a factor of 2 bigger than the angle parameters that XY that my minimized routine found. And that's because I had a difference in a factor of 2 between the way I was implementing the RXX and the RYY gates and the Qiskit approach. So once I found these angle parameters, I had to multiply them by 2 before I put them into my circuit here. And then to correct the phase, I needed a final RZ on my 0 qubit. But after I apply these gates, then here are my 16 computational basis states. Here are the real components compared between the target and what the circuit produces. And then here are the imaginary components between the target and what the circuit produces. So you'll see that in this case, the 4 non-zero states are all coming out now with the correct probability amplitude and the correct phase. So now we're correctly producing the ground state for the Heisenberg spin glass. The last thing that we have to do now is compute the energy. And the reason that this is slightly tricky is because the Hamiltonian contains terms that cannot all be measured in the same computational basis. The Hamiltonian contains ZZ terms and Z terms. Those can all be measured in the usual computational basis, but the Hamiltonian also contains XX terms and YY terms. So to measure those terms, we have to actually move those operators into the ZZ basis so that we can measure them. And so here's my routine that builds the circuit. The circuit as it is can provide us the measurement of all the Z-based terms in the Hamiltonian. So I compute those using the energy JIC function and the energy HI function over here. But then you also need to get the X components of the energy and the Y components. To get the X components of the energy, I have to translate from the Z computational basis to the X computational basis by applying a Hadamard gate to every qubit. In order to measure the Y components of energy, I have to do an RZ rotation around each qubit and then do a Hadamard. So this gives me the three different components of the energy. And if you look at the printout from running the program, you see the X, the Y, the Z components. And if you add them up, you get this minus 19.58, which matches the exact diagonalization of the energy eigenstate. So thank you very much. I appreciate you guys taking this problem so seriously. Your submissions were fascinating. I really enjoyed taking a look at them, and you guys did great jobs. If you have any questions, I'm happy to answer some questions. But I guess that's my presentation of the correct answer. Thank you very much.
안녕하세요. 양자정보연구지원센터 윤다입니다. 혹시 3번 문제에 대한 질문이 있으시면 영어로 해주시거나 채팅창에 작성 부탁드리겠습니다.
Is there a translation?
There isn't today, Denny. I think we're just waiting to see if anyone has questions, and then we're going to announce the winner of the overall
Okay.
challenge.
질문이 없으시다면 다음이 2024년 퀀텀 챌린지 수상자 발표를 진행하겠습니다. 이번 2024년 퀀텀 챌린지에는 총 80분의 참가자분들께서 참가 신청을 해주셨습니다. 그 중에서도 가장 우수한 점수를 받으신 순으로 장관상 1분, 총장상 1분, 센터장상 2분이 선정되게 되었으며 장관상을 수여하신 분께는 추후 오프라인 시상식이 진행될 예정입니다. 이 외에도 이전에 안내드렸던 바와 같이 문제를 풀으신 정도에 따라서 별이 지급되었고 문자 메시지로 기프티콘 상품을 발송드릴 예정입니다. 네, 질문 먼저 하겠습니다.
Hi, Danny. I think we have a question in the chatting room.
Okay, let me take a look. Yes. If the eigenspectrum, in fact, if you, I can go to the slide and, well, I don't think that's necessary. Yeah, but let me give you an example. If you have, for example, an eigenspectrum that contains eigenvalue -6 and a 0, it does matter how many times they appear. So if -6 appears 2 times and 0 appears 14 times, I would consider that a different eigenspectrum from if -6 appeared 8 times and 0 appeared 8 times. So yes, you should consider the degeneracy. You're welcome.
또 추가적으로 질문 있으실까요? 없으시면 그럼 이어서 수상자 발표를 시작하겠습니다. 첫 번째 과학기술정보통신부 장관상 부분에서는 오러벌드 20팀 성균관대학교 동훈님께서 수상하셨습니다. 성균관대학교 총장상 부분에서는 양자코인 팀의 카이스트 이동원님께서 수상하셨습니다. 마지막으로 양자정보연구지원 센터장상 부문에서는 참사리 팀의 고려대학교 박성근님, 윤인희 팀의 경희대학교 윤인희 님께서 수상하셨습니다. 모두 축하드리며 수상자분들께는 추후 개별 안내 드리겠습니다. 긴 시간 동안 2024년 챌린지에 참가해 주셔서 감사드리며 이번 대회를 통하여 양자 컴퓨터에 대해 더욱 많은 배움을 얻어가셨길 바라겠습니다. 그리고 방금 채팅창에 올려드린 만족도 조사도 작성해 주시면 감사드리겠습니다. 그럼 이상으로 2024년 3번 문제 해설 강연과 수상자 발표를 마무리하겠습니다. 감사합니다. Thank you all.